All right, so this is the rest of the solution that we started working on in class today for the equation, for the AP problem 2003, fourth question, so B4. And it has to do with this lab-based question of having a concave mirror that has a radius of curvature for 60 centimeters and trying to figure out a lab to make an image that is 4 times bigger. So if you are in the focal length, like what we were talking about in class, so we know the focal length is half of the radius of curvature. So let's put our object here. Let's see what the ray diagram says would happen. So the first one goes at it and goes back through the focal length. Okay, the second one is hard to do because you're in front of the focal length, so we kind of go to the center, bounces off, and so you end up with something that is bigger that appears onto the opposite side. Okay, and you would probably want to use a ruler to be better, right? Protractor, something like that. So we end up with a bigger one. So to experimentally find where you have the object distance that creates an image that is 4 times bigger, all you have to do is move the object around here or here, whatever, to find that image that is 4 times bigger. Okay, and you could use a ruler to figure that out, right? And a meter stick to measure that object distance. So when it comes to B, where you're trying to check off things, you can use a meter stick, you can use a ruler. You probably wouldn't use one of the lenses, convex or concave lenses. That just make things complicated. Probably still wouldn't want to use a convex mirror, because multiple lenses or multiple mirrors, and when you start mixing things, things get really, really complicated. Now this is a virtual image, right? Because it's upright. All upright images are virtual. Okay, which means that all inverted images are real. And this is an always type thing. Okay, always, always, always. So when it's offering you a screen and a holder, if it's virtual, there is no actual light rays that are converging, so you would not be able to measure it with or capture it with a screen. It would not happen. So you wouldn't want to check that one. So when you get to C and you're having to do a ray diagram, again, this is an experimental thing. So drawing a ray diagram like what we have up on the screen works the exact same way, or is all you really have to draw. To be to scale, that would require you to have to calculate how far things needed to be in order to create something that's 4 times bigger, and they're not asking you to do that. So you just draw a ray diagram as long as it gives you an image that's bigger and you're showing what you're supposed to be doing, then that's fine. When you get to D, checking everything that is there, right? It's a virtual image. It's a upright image, and obviously you're looking for something that's larger, so you would want to pick something that says larger than the object. Now part E is where it gets kind of interesting. So you complete your assignment and turn in your results to your teacher. She tells you that another student using equipment from the same list has found a different location for the lit candle. However, she tells both of you that the lab was done correctly and neither experiment needed to be repeated. Explain why both experiments can be correct. Well, you're searching for an image that is 4 times bigger, right? And our magnification formula says that HI over HO is magnification, and we're looking for that to be 4. Okay, but we also know that it could be the absolute value of SI over SO. Now, just looking at the equation, we can basically say that any ratio that produces 4 should be something that's possible for this experiment. Problem is that not every ratio that produces 4 is going to be possible when you're given a mirror of a certain radius of curvature, because of our other formula that 1 over F has to equal 1 over SO plus 1 over SI. Okay, both of these have to be valid, right, and still give you a magnification of 4. So how can this other team produce something that is 4 times bigger, but has a different image and object distance than you? Well, what if this team used their concave mirror in a different way? So here's our radius of curvature. There's our focal length. What if they put their object right outside the focal length? And let's do a ray diagram for what that would look like. So we have coming at it, goes through the focal point. Now what if we went through the focal point, came out straight? Wow, now we have an object that sits back here. What kind of object or image is it? It's a real image. It's definitely bigger, right? So maybe the closer you get to the focal point, you could fine-tune getting that image to be 4 times bigger, and you would be able to use a ruler to figure that out. But you would need one other piece of material, one other piece of equipment. You would absolutely need the screen for this experiment. You would need to have some kind of paper or something to be able to capture that image. And it would be upside down because it would be real. So this is also a ratio that would give you an SI over an SO that would give you 4. In this case, right here, your SO positive but small, right? While your SI is negative and much bigger. Well, and ray diagram doesn't necessarily show much bigger, but it would be much bigger. And you can go back to your notes to showcase that. While over here, we have an SO which is positive and small with an SI that is bigger and also positive, but would also give you a magnification of 4. So again, not every ratio works because not every ratio satisfies this equation as well. But with this particular type of mirror, you can produce 2 different types of images, one virtual and one real, and either one of them could satisfy this particular lab. Okay.